Videos. Are you getting tired of my voice yet? All right, too bad. You need to finish your lab work. So, in your last video, I showed you how to graph your data. Now, we've compared the two populations, and we can explore those statistics a little bit. But also, another question we have, or we can answer, is how accurate are these values in the first place? Like, how reliable was the data that we collected in the lab? The standard deviations are huge here. That's a red flag right away that we should be kind of skeptical of these results. But we have another piece of information, which is comparing these to reality, the expected value. What should we have gotten? So what we're going to be doing is we're going to calculate, I'm going to go over here to my red pen, because what we're going to calculate is percent error. Okay, the calculation for that is pretty straightforward, not too complicated. We're going to take the absolute value of your experimental value, and we're going to subtract the theoretical value. That's the literature value, sometimes it's called. Basically, this is the true value, what we would really expect. In this case, it's going to be off of the food label from the nutrition package. And then we're going to divide that all again by the theoretical value. And we're going to multiply this whole thing by 100%. That's going to give us our percentage. Okay? So if we come back over to our results, I'm just going to do cashews as an example. So I've got 1,815 calories per gram for that particular food. Now, how do I know how many calories per gram I should expect from a cashew? Well, take the package. The packages are still in the classroom for any of the foods that you tested. I'm going to look at the nutrition facts, and I'm going to find out how many total calories there are. In this case, cashews, one serving size has 200, and it says kilocalories. Sometimes on the package, it might just say calories, but food calories in general are big C, capital C, and that's the same thing. These are synonymous. However, this one of these big C food calories, I think I mentioned in the first video, is equal to 1,000 of the small ones. So we got to convert this 200, we're going to convert to small c's. 200 is equal to 1,000 of the small calories divided by 1 kilocalorie. So now I can cross out these units. So what this means is a serving actually has 200,000 small calories. Now, that's total calories per serving, and we want to compare back to per gram. So we need to look at how many grams are in a serving size. In this case, again, nutrition facts right at the top, serving size is a quarter cup, and it should have grams. In this case, it says 30 grams. So if I do 200,000 divided by 30 grams, all right, 6,666 calories per gram, right? So those are this one is my experimental value. That's what I actually got. And then my theoretical value is what I've looked up. I had to calculate it a little bit. But those are the values I want to compare, 18, 15, and 6,667. So we can go ahead and do that here. I'll just throw an extra, I've got percent error ready to calculate here. So I'm going to get, if I insert a column to the left, I can put the theoretical value, and for that it's 6,667. So percent error is simply going to be equal to this one minus that one. I need brackets though, because I need to divide that whole thing by the theoretical. I need more brackets, order of operations here, times 100 to give me a percentage. And now I'm going to get a whole whopper of percent error here, 73% error. Ouch. Meaning this value not at all close to this value. Yikes. So as I said, we can start to think about some reasons why your procedure would lead to such a low value compared to the expected. It goes back to what I said in the very first video about the assumption that what we have calculated here, Q, is the heat transferred into the water. But what we are actually comparing to is heat that was available and released from the food, not what got into the water. So there's room for some loss of energy there, and you can think about a lot of the reasons for that. And also, again, your huge standard deviations, I assume yours are just as bad, if not worse than mine, tell us that even from one trial to the next, there's huge variability. Now, we said before there's variability in biological systems, but not that kind of variability. This is pretty unexpected, and it hints at the fact that from one trial to the next, you have a pretty inconsistent procedure. And that's the other thing that standard deviation can do, is help inform how unreliable your data is if you're doing multiple trials of the same or similar things. In this case, we wouldn't expect different peanuts to vary too much in their energy content, particularly once we've corrected for the fact that we use different masses of the foods. So there you have it. That's the fourth and final installment. You should by now have got all of your data processed. You should have means and standard deviation statistics. You should have a graph and percent error to calculate for your data. That's a lot of data crunching for one day. Thanks for sticking with it. Have a great weekend. See you next weekend.